Hi, my name is Flynn Brennan. This is my paper on understanding dark matter using the Standard Model and Supersymmetry. So my introduction is, all of the matter that we know of in the universe only accounts for 5% of the mass in the universe. Dark matter is a type of matter that we cannot see, yet it is all around us and makes up 85% of the universe's mass. By using the Standard Model to describe how particles and matter behaves, as well as using the theoretical framework of supersymmetry, I will attempt to uncover the deep secrets that dark matter has held and reveal answers to questions asked by scientists for centuries. So, why this is interesting to me? The idea of dark matter has always been interesting to me. I enjoy thinking about what secrets the universe has that we are unaware of, and what puzzles are out there left to be solved. So, I decided to dive into the subatomic world and decided I would find out all I can about dark matter and the subatomic universe. So for background, I'll need to explain the Standard Model. Atoms are thought to be the smallest building blocks of the universe, but they're actually made of protons, neutrons, and electrons. Protons and neutrons can even be broken down into smaller particles. Developed in the 1970s, the Standard Model explains how these very basic building blocks of matter interact. In total, there are 17 elementary particles under the framework of the Standard Model. The figure on the right shows the 17 elementary particles in their individual groups, which are quarks, leptons, force carrier particles, and the Higgs boson. And the first group are matter particles, also known as fermions. So all matter around us is made of these matter particles. These particles occur in two categories called quarks and leptons. There are 6 quarks and 6 leptons, each occurring in pairs, or they call it generations. So the lightest and most stable particles make up the first generation. All stable matter in the universe, basically all matter around us that we can see and interact with, is made up from these particles in the first generation. The 6 quarks are paired as the up quark and down quark, followed by the charm quark and strange quark, then the top quark and bottom quark. The 6 leptons are paired as the electron and electron neutrino, the muon and muon neutrino, and the tau and tau neutrino. These matter particles are classified as having half-integer quantum spins, which I'll get into later. The next big category of particles are called force carrier particles. There are 4 fundamental forces in the universe, and the Standard Model includes 3 of the 4. The strong force, the weak force, and the electromagnetic force. It excludes the gravitational force, which I'll explain in a second. These forces are the result of the exchange of force carrier particles, also known as bosons. Particles of matter, fermions, transfer discrete amounts of energy by exchanging these bosons with each other. Each force has a boson that corresponds to it. The strong force is carried by the gluon, electromagnetic force by the photon, and weak force is carried by the W and Z bosons. There is yet to be found a boson corresponding to the gravitational force, and the theory of general relativity doesn't work on this scale, so that's why we exclude the gravitational force. These force carrier particles are classified as having whole number quantum spins. So next is the Higgs field. The chart on the right shows 2 electrons transferring a force carrier particle to one another and then changing directions. So next is the Higgs field. All particles can be represented as waves in a quantum field. Each particle has a quantum field that describes any change in that particle, and these quantum fields interact with each other. The Higgs field was proposed as another field present everywhere in the universe. This Higgs field was confirmed in 2012 with the discovery of the Higgs boson. So the Higgs boson is said that it gives elementary particles mass when interacting with it, and particles don't actually have mass. So particles moving in space interact with the Higgs field, and the Higgs field meets them with resistance, and this resistance creates mass, and therefore stronger particles have greater mass. So now, what is dark matter? Dark matter is an unknown type of matter that makes up the majority of empty space in galaxies and holds them together with its gravitational force, all while being completely invisible to us. So, we know we can't see dark matter, but what does this mean in physics? Dark matter is hypothesized to be made of undiscovered particles, elementary particles. These mysterious particles do not interact with the electromagnetic force, which means that it doesn't absorb, reflect, or emit light. It does, however, interact with the gravitational force, as seen by the strong effect it seems to have on visible matter. This also leads scientists to believe that dark matter does interact with the Higgs field as well, and does indeed have a mass. And this chart on the right shows visible matter making 5% of the universe, dark matter making up 27%, and dark energy making up 68%, which is different from dark matter, and I will not be explaining it, but it's a completely different thing. So one theory that could explain what dark matter is made up of is called supersymmetry. So supersymmetry is a theoretical type of space-time symmetry between two basic classes of particles, which are bosons and fermions. It claims that for every known particle in the standard model, there exists a particle with a different spin. This means that for every known boson particle with a spin of a whole number, there exists a new undiscovered fermion particle with a spin of a half integer, and vice versa. So supersymmetry solves many problems in quantum physics, one of them being dark matter. Scientists predict that the lightest supersymmetric particle would be stable and electrically neutral and would interact very weakly with the standard model particles. These conditions meet all the requirements for dark matter. So dark matter needs to be very stable and electrically neutral in order to not have a significant interaction with the standard model particles, yet it still gains mass by potentially interacting with the Higgs field or by some other reason. There's one thing with supersymmetry. There's a problem with it. It seems too good to be true. It solves way too many problems with physics, which we know can't work. However, there have been many tests done to confirm the existence of supersymmetry, and all of them have failed. So the Large Hadron Collider has been searching for these new superpartner particles for decades, yet in every experiment their existence has failed to be proven, which is detrimental to physicists because it makes them go back to the drawing board to explain all the problems that physics seems to have. So the topic of dark matter, though, is always in discussion, and physicists are constantly working on new theories that could hopefully one day unveil these mysterious particles. And on the right shows the Large Hadron Collider, which is located in Switzerland. It's huge. It spans like many miles, I think. So other potential theories for dark matter, lastly, I'll go over these theories. First is WIMPs, which are weakly interacting massive particles, or axions, a hypothetical very light elementary particle with no electric charge. Others include MOND, which is modified Newtonian dynamics, which alters gravity at low accelerations, or sterile neutrinos, which are theoretical massive cousins to the 3 known neutrinos that don't interact through strong, weak, or electromagnetic forces. And the chart on the right shows weakly interacting massive particles and how they interact with photons or different particles. And so the last slide is all my sources. And thank you for listening.